Hi, welcome to the last section in this chapter. We're actually going to spend 3 days here, and this is the first of 3 lessons on graphing rational functions. And if you'll recall, rational has the word ratio in it. Ratio means fraction. So a rational function is one that has variable in either the bottom or both the top and bottom. Okay, so we have in this one an odd degree, that is the exponent has just 1 in this one. So in odd degrees, so for third powers, fifth powers, you'll see that the rational function is broken up into 2 pieces, and if you think about them as being in quarter parts of the coordinate system, with a positive value on top, or a leading coefficient that is positive, the branches of this thing are in the first and third quadrants. When the degree is even, as this one is, still 2 branches. This is rational functions are always going to be broken up into 2 pieces, or at least 2 pieces. But in this particular case, those branches with an positive leading coefficient are in the first and second quadrants. I don't know how you guys think about this, but I always call this a volcano shape. And this one with the odd exponent, to me that looks like a butterfly. You'll probably come up with your own descriptions of what these look like, but in any case, 2 or more branches in a rational function. End behaviors for these guys are, well, you can see them very clearly. As x, it goes to negative infinity. So when we think about very small values of x, y goes to not infinity, but y approaches 0. As x approaches positive infinity, right, way out here, y also approaches 0. Now you can talk about behaviors as x approaches 0, and then it'll probably look a little bit more familiar to you. So as x approaches 0 from the left-hand side, or from the negative side, y is going to negative infinity. And finally, as x approaches 0 from the positive side, y approaches, so as x approaches 0 from the positive side, y approaches infinity. Okay, a lot going on in this function. For our even degreed function, we can make the same top 2 declarations. As x approaches negative infinity, y approaches 0, or gets very close to 0. As x approaches positive infinity, y also approaches 0. And then as we look at x, as it nears the x equals 0 mark, so as x approaches 0 from the negative side, y approaches positive infinity, grows very fast right up in there. As x approaches 0 from the positive side, same thing, y approaches positive infinity. So these are a little bit different. Many rational functions have asymptotes, which is a lovely math word, but I call those lines of avoidance. They're lines that the function approaches. It really tries hard to get to them, but it just can't. So for me, lines of avoidance. Today and tomorrow we're going to be looking at how to find 3 types of asymptotes in rational functions, and the goal of this is to learn to graph them better. We're going to look today at vertical asymptotes, so vertical lines of avoidance, and you can see in this function x equals 0 is one such line. Okay? It approaches x of 0, but it can't get there. We also will look at horizontal asymptotes, and both of these functions have horizontal asymptotes as well at y equals 0. Okay? It tries to get to a y of 0, but it just can't make it there. Finally, we will look at a slant asymptote, and that may be something that's new to you. Probably talked about vertical and horizontal asymptotes in your Algebra 2 class, but slant asymptotes, which will be our topic in the next discussion, may be somewhat new. So let's look at what causes vertical asymptotes. And folks, what really happens, a vertical asymptote occurs when there is a non-factorable something that can't be factored out, a non-factorable discontinuity, it's called. And that, my dear friends, is just a long way of saying there's some value of x that causes the denominator in the function to be 0. Some value of x that makes the denominator equal to 0. And the whole business about non-factorable means it can't be factored away. If that's true, you'll notice that there's a vertical line, or it could be more than one, that the function approaches but can't touch. All right, and I would just remind you, just a little asterisk up here, asymptotal behavior really means what's happening as x gets very big or very small. So as x approaches infinity at either end, that's when you talk about asymptotal behavior. I said here that a vertical line that the function approaches but can't touch, that's pretty accurate, but there are some cases, some functions, where in certain places in x it may cross that asymptote, but in others, as you get farther out to positive or negative infinity, you'll see that it approaches there and never will touch again. So, all right. This says that we want to determine the vertical asymptotes for the functions, the rational functions that are shown here. And I would ask you to look at the first one, y equals 3 divided by the binomial x minus 2. Well, this can't factor since there are no factors of x minus 2 in the top. So we are going to have a vertical asymptote, and it will be created by an x that will make that denominator 0. So this is how I write that thing. There's a vertical asymptote at, and it is the line where x equals, what value will make this 0? Yep, 2. Where x equals 2, this will have a vertical line of avoidance. I want to just take a minute to check out in the calculus. I want to enter a function at 3 divided by, and then it's the quantity x minus 2. Alright, the standard viewing window will be good for us to see this. So, yeah, you can see at x equals 2 right there, that function doesn't exist. Okay? It can't exist because that would create for us, think about why it's impossible for it to have a value there. We'd have a divide by 0 error on the bottom, and that's not allowable. What do you think about this one? The function says 5x over the quantity x minus 2 squared. This also should have a vertical asymptote at x equals 2. You can see that there's going to be a problem area there, but this might be an interesting one to look at. I want to go ahead and go back to the graphing calculator, and let's just scope that one out for a minute. So I'm going to go to a new graph page. And it was x divided by the quantity x minus 2 squared. All right, and yep, right here at x equals 2, we have that line of avoidance. If I were going to talk about the shape of this graph, to me this is that volcano graph. You can see that it shoots up to positive infinity on both sides of the line x equals 2. So a vertical asymptote happens there. Our next function, y equals x squared minus 4x plus 3 divided by the quantity x minus 3. I know that something is going to happen in this function when x is 3, but this is the first place, folks, where we are going to be able to factor the top or bottom. This one was broken up into factors, but 5 minus 2 is not divisible by the quantity x minus 2, so it didn't matter there. It is going to matter here. X squared minus 4x plus 3. If you think about your box method, x squared is what we know, and we are factoring this thing. So we also know the 3. You go to the x and you think to yourself, 3 times 1, so it's numbers that have to multiply to make 3. They have to add to make negative 4. And there's only one way for that to happen. That's negative 3 and negative 1. So a negative 3x here and a negative x here. X and x come out. The only way we can get that minus 3x is if there's a minus 3 factor. The only way we can get negative x is if we multiply by negative 1. So that top factors into x minus 3, x minus 1. And you can see that the quantity x minus 3 factors out of top and bottom. So this is not going to cause an asymptote. Instead, this will have what I would call a hole, or a point discontinuity is the correct term for it. A point discontinuity at x equals 3. I want to show that to you on the graph because you may be surprised by what this function looks like. Quadratic divide by binomial. And we think quadratic, we think parabola. This is not going to look like that. This is going to have the appearance of what's left after you cancel or divide out that x minus 3 quantity. Let's look at that real quickly. New graph page. And what we had is, you got to use the parentheses here, x squared minus 4x plus 3, x squared minus 4x plus 3, all divided by the quantity x minus 3. All right, and let's take a look at that graph. Aha, it does. It looks just like a line. That's what's left over after you factor out that x minus 3 in both places. The line is x minus 1, and you can see that. It is an increasing line with a slope of 1 that goes through the axis at 1. What we need to know, or what I want to know, is what does happen when x is equal to 3. And it's not easy to see on a graph here. Instead, I'm going to go to a table because I can see it a little bit better there. I know that something happens when x is 3, and look there, for sure. When x is 3, this function is undefined. And really what that means, folks, let me get the table out of there. What that means is that when x is exactly 3, there's a hole in this function. There's a spot where it just doesn't exist. Okay? Our calculator can't show that unless we zoom in very closely, but I just want to make sure that we get this clearly in our minds. When that function hits x of 3, and it came through looking like this, there is a spot where it just doesn't exist, and then it continues on its merry way. So we had to be really careful here, factor if possible, and then cancel, factor and cancel. We did have an anomaly, some strange thing happened when x was 3, but it wasn't the asymptote that we expected, and we would not know that unless we factored. So I can't say that too many times today. Here's our next topic, horizontal asymptotes. There can be a horizontal asymptote when the degree of the numerator or the degree of the top is less than or equal to the degree of the denominator or the degree of the bottom. Okay, I use the right math language, but then I write in my plain English. So we can get a horizontal asymptote when the degree of the top is less than or equal to the degree of the bottom. If that's true, that you will notice that there is a value of y that's avoided. And that happens again when x is very large or very small. Okay, there's a value of y that's avoided as x goes to positive or negative infinity. All right, to find horizontal asymptotes, this is what you do, and this is going to sound weird, but we'll see it in a moment. You divide each term by the largest power of x in the denominator. Sorry, it takes me a long time to write that. You divide each term by the largest power of x in the denominator, and then determine what will happen to each term as x gets really big or as x gets really small. So I want to just have you think about this for a minute. If I'm going to divide everywhere here by x, so I'm going to think x divided by x on top, x divided by x on the bottom, and 1 divided by x on the bottom. And folks, as you do the simplifying here, do the math, anything divided by itself is 1. So on top, that comes out to be 1. On the bottom, x over x is also 1. But this 1 over x, folks, think about that. What happens to the fraction 1 over x as that denominator gets really big or really small? So think about this, 1/100th. How does that compare, say, to 1/1,000,000th? Which is the smaller? This one for sure. If we break 1 up into 1,000,000 pieces, they are tiny, 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 tiny pieces. In fact, as x gets bigger and bigger and bigger, this thing approaches 0. It gets smaller and smaller and smaller. So technically what we're saying is when x is really, really big or really, really small, then this just doesn't matter. It's going to go to 0. And the y asymptote, or the horizontal asymptote in this, is the line y equals, well, it's 1 over 1 minus 0, so that's y equals 1. This one has a y asymptote, a horizontal asymptote, at the value y equals 1. Now that's worth checking out. So I'm going to get back in here, get a new graph page, and what we were looking at was, now I forgot the function, x over x minus 1. So I want to get a graph page, and I want x divided by the quantity x minus 1. All right, let's take a look at this one. Okay, we said it would have, well, it does have a vertical asymptote, by the way, at x equals 1, and you can see that here. But what we just found was the equation for this y asymptote. See how it slides along that line y equals 1? It tries to get there, it just can't do it. So this one has a vertical asymptote at x equals 1, but it also has a horizontal asymptote at the line y equals 1. Let's try that again, because that is kind of an odd concept. It says that you divide each term by the largest power of x in the denominator, and you do that if the degree on top is less than or equal to the degree on the bottom. Well, this is less than. So I should be able to find that horizontal asymptote by dividing each term by x cubed. So I'm going to think 2x squared divided by x cubed. And I want you to think about that. The 2x powers on top knock out 2 on the bottom. This is going towards 2 over x. And we just had a whole big discussion about what happens when the denominator in that fraction gets super huge or super small. Folks, that's headed to 0. On the bottom, if we divide by x cubed in both places, Well, this one, x cubed over x cubed, is 1. That's going to 1. This, anything, well, if over x to the first power heads to 0, this just gets there faster. 8 over x cubed is going to 0, and it's going really fast. So here comes the equation for our y, or horizontal asymptote. It's what's left over when x gets super big or super small. On top, 0. On the bottom, 1 plus 0. So our horizontal asymptote in this function is y equals 0 over 1, or just 0. The y equals 0 line will be the asymptote in this function. Let's go to a new graph page and look at this one. The function that we're interested in was 2x squared divided by the quantity x cubed plus 8. Okay, 2x squared divided by the quantity x cubed plus 8. And what we're saying is that we should see a horizontal asymptote at y equals 0. And I believe, folks, that you can see that. There is a line of avoidance here at -2, because if x is -2, then this becomes -8 in there. So there is the vertical asymptote, but the one we're interested in, the one that we just found, is that horizontal asymptote at 0. And I just want to point out to you, in this function, you can see that it has a value of 0 right there. However, when x is getting really big or x is getting really small, this thing approaches 0. So asymptotal behavior, always you're thinking about what happens at large values of x or small values of x. And this has a horizontal asymptote at the line y equals 0. Great. Let's see if we can look on this next one. The function is 3x squared over x. And we want to divide each term by the largest power of x in the denominator if the degree of the top is less than the degree of the bottom. That's not the case here. Folks, this one has no horizontal asymptote because we've got a higher degree on top than on the bottom. So no horizontal asymptote in this one. So that was the trick question. All right, let's go on and see. I think we're going to just, now we get to the big deal today, which is graphing these functions based on their asymptotes. That helps us know where to hang the framework of a graph. So we'll ask you to look at this one. Will this have a vertical asymptote? I seem to think so, since I wrote that. Yep, the thing that will create a vertical asymptote on this is if x is 5. You can't factor an x out of each term, but if x is 5, there's going to be a problem. And when I'm graphing, I show that, folks, with a dashed line right where that asymptote is at. So we've got a line of avoidance at x equals 5. We need to check for a horizontal asymptote because these degrees are equal. So I'm going to do my little scratch work out here. Divide each term by the highest power of x in the denominator. And I think you can see what's happening. On top, we're going to have 1 because x over x is 1. Here we have x over x, 1, minus 5 over x is going to 0, so we're going to just say it doesn't even count. It's so small that it's negligible. Our horizontal asymptote then is the line, and so this is how I write that. Horizontal at y equals, well, 1 over 1 is 1. So we have a horizontal asymptote right in here. Now, here I'm going to just use my powers of deduction, okay? We have a positive leading coefficient here. The degree of this function is 1. So it's an odd function. It should have 2 branches, one in the first quarter, one in the third quarter. This is my guess for what that's going to look like. So I'm estimating. And I am always going to go back here and check it out. New graph page. And the function that we were interested in was x over x minus 1. because every once in a while you can be surprised by one of these. It won't act the way you think it should. Let's check this one though and see. Oh, sure enough, we've got the vertical asymptote at x equals 1, the horizontal asymptote as y equals 1, and the two branches of that function are arranged in the first quarter and the third quarter, which is just what we expected. I like it when things work out that way. Here's our next one. We have x cubed over the quantity x minus 2 times the quantity x plus 1. Folks, this is nice. It's already in factored form, and I can see that nothing is going to factor out of both top and bottom. So I am good to talk about vertical asymptotes. I know where those will happen at x equals, well, it would be 2 and negative 1. So x of 2 is that line, x of negative 1. I don't know how well I'll be able to sketch that there. As far as horizontal asymptotes, the bottom of this has 2 powers of x. So this degree, 3, is bigger than this one, 2. This is not going to have a horizontal. No horizontal asymptote in this one. So now it's a matter of deciding what we think it's going to look like. And I'm not quite sure. But I do know that we've got 3 pieces of plane here to work with. So I'm thinking that there's going to be something in each part of the plane. This is where I'm going to reach for that calculator. So I'm going to go ahead and minimize my window so that I can see the calculator. Get a new graph page. Add a graph. Okay, that's what I want. And I need x cubed, x raised to the 3rd power. I need that divided by, and I'm going to open 2 sets of parentheses here because I need to divide by everything on the bottom. It just happens that they're shown in parentheses. So x minus 2, and now I need to move past that first parenthesis and open a second. X plus 1. All right. X cubed divided by. Good. So let's see what we see here. Ooh, that's weird. And I'm not sure that we're seeing the whole thing. We've got 1, 2, 3 pieces of plane for sure. But I want to just adjust that window just a little bit so that we can see what's going on up in the corner there. So I'm going to tell it to go from negative 10 to 10 in x's, and I'm going to adjust these to go negative 10 to 10 as well. So negative 10 to 10 in y's, just so that we can get a slightly better picture of it. Okay, so you can see there are 3 parts to this function. We've got a curve down here. We've got kind of a ribbony thing right there, and another curve that grows up here farther. We are sketching this graph, so I'm not afraid to say I'm not sure exactly what that point is, although I think I could find it out by looking in a table. I'm going to say I know we've got a branch in here, we had a ribbony thing in the middle, and we had another branch doing that thing. Interesting function, that one. Very neat. Okay, let's go back. This is the last task in the lesson today. The graph below, it says, is a transformation of y equals 1 over x. So this is its parent. We want to know about an equation. So I would submit to you that it looks to me like the center point, the origin, if you will, has moved. It's moved left and down. And we can write an equation for this function if we can find out how far left it's gone and how far down. So I'm going to ask you to use your best judgment here. And I know that there is a vertical line of avoidance right there. Folks, that looks like x is at negative 1 to me. Now, if that's the case, then my function has got to look this way. Y equals, we moved left 1, x plus 1. right? Because remember, when it's with the x, when it's part of a quantity, it's moving the opposite direction of what you think. So this is at x minus 1. That means we have a plus 1 in the rule. Now to move this function down, how far down has it gone? Farther than 1. It's gone 2 down. So it has a horizontal asymptote right there, if you will. But I think this thing, if you think about it in terms of transformations, it's moved down 2. We can say that, because remember that just the constant part moves it up or down the y-axis. 1 over x plus 1 minus 2. Now, it wouldn't be me if I did not check that out and make sure that I guessed right. So I'm going to go ahead and look. I'll tell you, I don't always guess right. But I think that this looks pretty straightforward to me. We want 1 divided by, and it's the quantity, x plus 1. X plus 1. And then we want the whole thing shifted down 2 units. Let's see what we think about that. Not bad. That looks like a pretty good representation there. I think we hit it right on. We are left 1 and down 2 for this function. And folks, that's the end of our lesson for today. I know this has been a long video, and I thank you for your patience. Tomorrow we'll be talking about how to find slant asymptotes in these functions. I'm going to ask you to look at the U try right now, and I hope that you all have a great night.